All right. Guess we can just jump right into it. All right. So tonight we are going to be going over some chemistry, obviously, but we're going to be going over Unit 2 of AP Chem, which basically focuses primarily on structure and really what makes certain molecules act the way they do and how their structure impacts their behavior and other aspects of their chemical nature, along with how bonding works and how ionic and covalent bonds work and all of those fun things. So let's just jump right into it. And then if you guys want to ask any questions, feel free to use the chat or use the ask a question box. You know, we kind of got a smaller crowd tonight, so you know I'll be watching the chat. So yeah, feel free to talk amongst yourselves. All right. So first and foremost, you know, feel free to follow us on social media for all the streams that are coming up, all the IP Chem streams and other APs you might be taking. We've got Twitter, Instagram, YouTube. We always post whatever streams are coming up, so be sure to drop a follow. All right. So a little outline of what we're gonna go over tonight, and it might look like a lot, but really all of these topics are interconnected because of the fact that they're in the same unit. They're all related to each other in some way, shape, or form. So the first thing we're going to talk about is really the types of chemical bonds, right? So covalent bonds, ionic bonds, and metallic bonds are the major three types of atomic bonds that we're really going to be talking about in this unit. Then we're going to talk about intramolecular force, potential energy. Basically, why do atoms bond? Why do they bond instead of just sitting alone as their own atomic selves? Then we're going to be looking at the structures of certain types of solids, right? We're going to be looking at ionic solids, things like salt and other types of salts, and then structures of metallic solids, so like a bar of steel, for example. Then we're going to talk about what's arguably the most important concept in this unit, which is Lewis dot diagrams. Basically, if I show you a molecule, how can you draw out what it looks like? And then from there, we're going to talk about resonance and formal charge, just a couple aspects of Lewis dot diagrams that are really important to know. And then we're going to talk about VSEPR and bond hybridization and bond geometry, which are all really important to understand for this unit. All right. So first thing we're going to be talking about are the types of chemical bonds. Just jump right into it. So the first and most major and important type of chemical bond that you're going to encounter on the AP exam and in chemistry in general is the covalent bond. So really, you might have learned this in honor or in other chemistry classes, but basically a covalent bond is just when electrons are shared among atoms. And so basically it's where two shells will overlap and they will share the electrons in order to fill the octet or fill the orbital of another atom. So for example, here we see the H2 molecule being formed. We see that in each of these hydrogens, we have one individual electron in the 1s shell, right? Our orbitals from the previous unit. So then what happens is we take these half-filled orbitals and they will react and overlap to form two full shared 1s orbitals, essentially forming the H2 molecule. And so it's really a direct form of bonding, right? These two molecules are directly overlapped, right? And the reason they do this is because they need a lower potential energy, right? When they're alone in this state with just that one electron, there's a lot more stored energy in their, they have a lot more stored energy. And then when they bond, the potential energy lowers, which is better for the system as a whole. We'll get more into like the specifics of covalent bonding and how bonding really works in terms of orbitals and other forms of bonds such as sigma and pi bonds later in this stream, but that's really the baseline of what a covalent bond really is at its core, just shared electrons among atoms. And then for those of you who are just now joining, if you guys have any questions, feel free to drop those in the chat or really in the ask a question thing, really anywhere. There aren't many people tonight, so feel free to, All right, so another really important part of covalent bonds is that they're not usually perfectly shared, right? The electrons are not perfectly shared among the atoms, and this is due to a property known as electronegativity. So electronegativity formally is defined as the measure of the tendency of an atom to attract a bonding pair of electrons. Basically, what that means in terms of layman's terms, it basically means how hard does a certain atom pull on electrons, right? So, for example, and there is a periodic trend for this. It increases going to the right and increases going up. So, for example, the most electronegative element on the periodic table is fluorine, right? It really tugs at those electrons. And because of that, if you bond two atoms together of different electronegativities, you're going to see an effect where one atom essentially pull the electrons harder than another, causing what's called a polar covalent bond. So that's what we see here. So here we see a polar covalent bond, right? An unequal distribution of the electrons around the covalent bond. However, if you do have a diatomic molecule, something like H2, O2, F2, that's where you'll see a nonpolar covalent bond because they have the same electronegativities. So does that make sense to you guys? That, I know I kind of went through that kind of quickly. So if that didn't make sense, drop in the chat, thumbs up, thumbs down. All right. I guess that means we'll move on. All right. So here are perfect. Okay. So here are some examples of, okay, there probably is just a little bit of lag. That's not good. So here are some examples of polar and nonpolar covalent bonds. Here we see, for example, hydrochloric acid, the structure of hydrochloric acid, and you can see that because chlorine pulls on those electrons a lot harder than hydrogen does, you'll see what's called a dipole moment in this direction, right? You'll have a negative side over here and a positive side over here. Same thing with ammonia, right? Nitrogen pulls on those electrons a lot harder than does hydrogen. And so you see the electrons being pulled this way. And so you'll see a negative side over here and 3 positive dipoles right there. Same thing with chloromethane. You'll see the dipole going this way because chlorine, again, pulls on those electrons. However, you will also have a nonpolar molecule when the structure and the geometry of that molecule is symmetric. So, for example, boron trifluoride is a perfect symmetric molecule, meaning that it is nonpolar. And that's because if we look at these dipoles, right, we see fluorine's pulling those electrons in this direction, this fluorine's pulling them in this direction, and this fluorine's pulling them in the other direction. Those dipoles will cancel each other out, meaning that overall, the actual dipole moment of that molecule is 0. There's no actual polarity to the molecule as a whole. So does that make sense to you guys, the whole concept of those charges canceling out in a symmetric molecule to form a nonpolar molecule as a whole? Again, just drop a thumbs up, thumbs down. Perfect. All right. And I'm going to be doing that a lot through the stream, just to make sure y'all are, picking up what I'm putting down. So same thing here with, I'm not sure what that would be named, I guess, tetrachloromethane, right? You see there's charges going this way, and then these 3 directions. Those will all cancel out because they're the same strength and opposing directions, meaning that they'll all cancel out and cause a net dipole moment of 0, as opposed to these bonds, which are not symmetric, right? We've got the chlorine up here, that's different than these. We've got, we have asymmetrical structure here, and then HCl, that's just a single bond. That can't be symmetric nor non-symmetric. So here is a little practice question that you might see on the AP exam. It definitely could be a multiple choice question. And it's asking which of the following bonds exhibits the highest polarity. So you have H2, you have H bonded to a fluorine, you've carbon double bonded to an oxygen, and carbon bonded to a fluorine. So just take a guess, which of those basically has the biggest difference in electron pull? Basically, which of them? Yeah. All right, Hannah says B. Any other guesses? B? Okay, we're seeing B is the general consensus. Here, I'll wait for maybe 1 or 2 more people to chime in. Give you guys another couple seconds. All right. So yeah, the answer is B, right? And the reason that the answer is B is because, so let's go through these one by one, right? H2, we see that those are the same atom on either side, meaning that this, that that letter A has no polarity whatsoever, right? There is really no polarity between hydrogen and hydrogen because of the fact that they're the same atom, right? With C, you see that C double bond to an O, carbon and oxygen have relatively similar electronegativities, just if you look at the periodic table, right? If you look at the periodic table, carbon and oxygen are right next to each other, or pretty much right next to each other. There might be one or two elements in between. So that means that there really isn't going to be that much difference in pull of electron between carbon and oxygen, meaning that while this bond will be polar, oxygen is more electronegative, it won't be the most polar. And then looking at D, carbon bonded to fluorine, the same thing applies, where carbon has a higher electronegativity than hydrogen does, and so hydrogen bonded to fluorine will have the highest polarity out of 4. So does that make sense to you guys? Is that, do you understand this question? Could you answer it on your own? The dogs are going crazy right now. Perfect. All right, so let's move on. All right, so ionic bonding, right? So ionic bonding is pretty much just as it says. It is bonding that creates ions, right? So traditionally, it's described as an electron transfer, right? The electron in that sodium ion will move to fill the octet of that chlorine atom, thus forming a sodium plus and a chlorine minus, and those two opposing charges stick to each other, right? Opposite charges attract. However, the thing with ionic bonding that you have to remember is that there's technically no such thing as a truly ionic molecule. There are molecules such as sodium chloride that get incredibly close. However, there will always be some covalent character to it. So, for example, take aluminum as an example. Aluminum fluoride, for example. I think that's what it was. The aluminums have 3 electrons that they need to get ripped off of them because they're technically a metal. That takes so much energy to rip 3 electrons off that aluminum that in reality, there's going to be some form of a sharing situation. So while when you see metal, non-metal in a formula, think ionic, also remember that there really isn't a truly ionic molecule where there's a direct, this is no electrons, this is 8 electrons. It's usually this has no electrons, the electrons like are here, and then this is the ion that also is formed, causing them to stick together. And we'll go over what makes the attraction between them stronger or weaker, depending on the charges and the sizes of the atoms. And we'll get into that a little bit later. All right, the final form of chemical bonds that we're going to be talking about tonight is metallic bonding. Right, so metallic bonding isn't really that covered on the AP exam, but you do need to understand it. Basically, in a metal, the electrons in the orbitals are delocalized. They can move around across the atoms as much as they really please. And this kind of explains a lot of the features of metals, right? They conduct electricity in the solid phase. They're ductile. They are malleable, at least at high heats, right? So that explains a lot of properties of metals. And the reason for these properties is because of metallic bonding, this electron C, as a lot of people call it. Really, the most important thing to take out of this is that metals can conduct electricity really well in the solid phase because of this constant electricity moving through them. All right. So the next topic that's covered in Unit 2 is intermolecular force and potential energy. So we've just gone over 3 major types of chemical bonds. So now we're going to talk about why do these bonds happen in the first place and what forces within the molecule and within the atom cause this to happen. And the main force behind bonding is potential energy. Right. So let's take a quick look at a graph of potential energy and bonding right here. So here we see a graph where the y-axis is the amount of potential energy, where here's 0, and this is the distance of separation. So here you see they're separated, they're overlapped a little bit, and now here they're overlapped a lot, and then it starts increasing. So let's start talking about the different parts of this this chart. So here we see when the potential energy is near zero, they're separated, right? We have potential energy here, here. However, there's no bonding happening, so the potential energy is not minimized. And then we see as they get closer and closer together, we start to see a dip in the potential energy. The bottommost point represents stabilization. Yes. So we'll get to that in just a second. When you start getting closer and closer, and then you hit here, right? We hit a minimum point. This is where the bond will occur, right? This is as close as the atoms will get, right? And so the reason for this is that you can see once we reach this point, we start to increase again. And the reason for this is because, remember, the electrons are still swarming around this atom. And so when you take these clouds and you get them just close enough, they start bonding, and the potential energy is pretty good. But then you get them too close, and you see electron-electron repulsion and proton-proton repulsion that pushes up the potential energy super high. It almost looks exponential. And so that's actually why certain bond lengths exist, because the optimal potential energy for each bond is different, leading to a differing bond length for differing bonds. Excuse me. So we can, when we look at this, we can start to find some trends in covalent bond length and bond energy, right? So if you have a really high bond length, the potential energy is not going to be as low, meaning it's going to take a lot less energy to break that bond, right? You can also just think, it's a single bond, and so you can break it easily, right? So when we look at a single bond, we see that in terms of bond energy, it's the lowest, right? It only has one overlapping orbital, and you really only have to break that one. And the bond length will be the highest because of the fact that there isn't a lot of constraint on it, right? You're not going to have a bunch of electrons bonding. You're just going to have these two clouds that are overlapping, meaning there's a little bit of wiggle room in the length being longer. So then when we move down to a double bond, this is the medium, right? Bond energy will be medium, and bond length will be medium. And then when we get to the triple bond, we can see that the triple bond is going to be just logically stronger. You've got 3 Coulombs there, so you're going to have to use more energy to actually break those bonds. Similarly, as we start to make more bonds, the atoms are going to have to get closer and closer together in order to get that minimized potential energy, meaning that the bond length measured in angstroms, that's what that little fancy A there is, will be shorter for a double bond and then a triple bond. So does that make sense? When I took AP Chem, I kind of just memorized this bit and didn't really understand why. So it's definitely a difficult topic to kind of wrap around your head. It kind of makes sense logically, but at the same time, it kind of doesn't. So, if any questions you guys have, just let me know if that makes sense to you guys. Perfect. All right. So let's move on. All right. So here's another question. And you'll see I kind of put a question or two in each of these units. Here's another AP style question, right? So which of the following lists bonds in order of increasing bond energy, right? So we want the lowest to the highest bond energy. So just give it your best guess. All right, Matthew says B. Hannah says B as well. All right, let's see if anyone else has any other guesses. All right. Well, the correct answer is B, and we know this because we see, looking through these 3 options besides none of the above, C is just out of order. Double bond followed by a triple bond, followed by a single bond. It's just out of order. It's not going to be increasing nor decreasing. Then if we look at A, a student who would choose A would be looking at bond length, right? So nitrogen would be the shortest bond length, oxygen longer, hydrogen even longer. Or they might just have confused the rule. But B, because we're going single, double, triple, will have a higher bond energy as you move forwards. So that's why B is the correct answer in terms of this question. So the next thing we're going to be talking about with this topic is ionic solids and Coulomb's law. Right, so Coulomb's law, it might look really scary, but all it's telling us is that the electrostatic force, or basically how strong two ions are held together, right, is proportional to their charges and inversely proportional to the distance between them. So basically, if you have really high, highly charged atoms with little distance between them, meaning they're small, it would imply a stronger ionic lattice energy is what it's called. Whereas if you have lower charges and big atoms, you're not going to have as strong of an ionic attraction. Right. So do you all understand Coulomb's law in terms of just what it tells us about ionic compounds? In terms of we want the strongest bonds, ionic bonds will have small atoms, big charges, right? So let's give another question a try. So which of the following compounds has the highest lattice energy, right? Which of the following compounds basically is held together the strongest according to Coulomb's law? And this is a question, not exactly, but I've seen essentially this exact question on AP exams. And it's really important to understand Coulomb's law from a conceptual point of view. You're not going to have to calculate anything ever, however, using Coulomb's law. So just give it a guess. And these usually take a little while, but there's one that you should be able to knock out right away in terms of having the lowest lattice energy. So just give it a guess. All right, so Matthew's guessing C. Any other guesses? All right, Hannah says A. All right, so A and C are both not the right answers. The answer is B. So I'm figuring the first thing you guys did, and if it's not, let me know, is that you knocked out D right away. CH4 is just not an ionic molecule, and so it won't have a lattice energy, period, right? So that one you can knock out right away. So now let's start looking at these three, right? And you really do want a periodic table to do this problem. I'm actually going to pull one up right now. So let's start going through these. So potassium iodide. We see that potassium and iodide both have +1 and -1 charges. However, they're relatively large, meaning you're going to have a high, right? We see you look at the distance. Lithium fluoride, lithium and fluorine, they're small. However, they are +1 and -1. However, magnesium oxide, if you look at magnesium and oxygen isn't that much bigger than fluorine, significantly, and magnesium the same, right? They're bigger. However, their 2+ and 2- charges are going to increase the lattice energy more than distance. So that's why magnesium oxide would be the correct answer. And in fact, let me pull up something that an actual chem teacher said. Right, she says that B is correct because the charge is 2+ and 2- in the ions. Right, so even though magnesium and oxygen are bigger, yes, than lithium and fluorine, they have the higher charge. And so unless they're significantly larger, and they'll make it obvious on the AP exam whether you should take really distance into account, that's when you, that's why B would be the correct answer. So do you understand why B would be correct and not A or C? You're definitely going in the right direction. So I'm glad that you were looking at the distances. However, those 2+ and 2- charges are just going to be a lot more attracted to each other. Especially because if you think about the numbers, you're going to have quadruple the number on top, right? You're going to have 1 over here versus 4. So again, you can see that it really does increase the 4. All right. So let's start talking about our next topic, structures of ionic compounds. This one is relatively quick. I know for a fact it's one slide, one thing, just quick and easy. And you've probably heard about this 100 times in all your chem classes, right? So when you look at an ionic compound, you remember that you're going to have positive and negative ions, right? And again, you want to reduce repulsion, right? You want to get as tightly packed and as ordered as possible. So what atoms will do in ionic bonds is they'll form what's called a crystal lattice or an ionic lattice. The word lattice is what you really should pick up here. And so you can see we have a weaving pattern of positive, negative, and here's a little cross section. We can see that there are strong electrostatic forces between the oppositely charged ions, right? That plus will get surrounded by negatively charged particles because of the fact that opposite charges attract. And so by forming this lattice, they will maximize the attraction to themselves while minimizing repulsion, right? There's going to be some repulsion here, right? There's going to be some repulsion all along here. These negative ions are going to repel themselves. However, and same with these positives. However, this structure, because of the fact that each ion is surrounded by what it's attracted to, it maximizes attractions and minimizes repulsions. Does that make sense? That's really all this unit is, just saying that ionic compounds will form a crystal lattice in order to maximize attraction and minimize repulsion. All right, perfect. All right. Next one is, again, pretty simple. It's on these structures of metallic compounds, right? So here, we're going to be talking about different types of things called alloys, right? So basically what happens when two metals combine because of the way their bonding works, right? This isn't going to be a chemical reaction type of thing. This is going to be a situation where metals will fuse to form, yeah, exactly, Hannah, substitutional and interstitial, I think that's how you pronounce alloys, is exactly what we're going to be talking about next. So let's just jump right into it. So there are two types, as Hannah said, two types of alloys, right? We have interstitial and substitutional alloys. So these two are not mutually exclusive. You can have both an interstitial and a substitutional alloy in the same metal. However, the difference is in their definitions. So in an interstitial alloy, smaller atoms will fill the interstitial spaces between larger atoms. Kind of think of it as super tiny balls kind of like in between the metal. In substitutional alloys, you have just that. Similar size atoms replacing the atoms of another metal in that electron sea. So for example, what type of alloy would A and B be, right? So just say like A is blank and B is the other type. Just give you guys a couple seconds to think about it. Just tell me which of these is interstitial, which of those is substitutional. I don't know if you guys can see it, but the left is A and the right is B. So just say which one is interstitial, which one's substitutional. All right, so Matthew's saying that A is interstitial. A is substitutional because we see that, oh, okay, perfect, Matthew corrects himself, right? B is interstitial because you can see these smaller atoms here, and all these other places going in between the atoms of the metal, whereas in A, you see actual substitutions taking place. All right. So that's really all this unit is, just talking about what an alloy is and how they work. So some common examples of alloys may be steel. Steel is really the big one. Other examples might be bronze. So those types of things that you hear about, those are alloys, right? They're mixtures of metals in an atomic fashion in order to form these new substances. All right, so this is the big one right here. This is what we're about to get into. And this is really the most important part of this whole unit. Because if you can't draw a Lewis dot structure, this whole unit is going to be a struggle. So I'm going to take you step by step on how to draw a correct Lewis dot structure, and then we're going to do some practice with it. All right, so let's just jump right into it. So the first part of a Lewis structure is that you got to know the order in which the atoms are connected. So for example, for our first example, we're going to be drawing the structure of hypochlorous acid. So hypochlorous acid, it's HClO. However, the bonds are actually in the order HOCl. And on the AP exam, when they ask you to draw a Lewis dot structure, this will generally be given to you, right? So if they want you to draw some Lewis dot structure, they'll show you the general composition of the molecule. However, you will learn quickly some just common shapes and some common ways to draw Lewis dot structures in such a way that you might not need that all that often, but it will be given to you, at least on free response questions. All right, so our second step when we're doing a Lewis dot structure problem is we want to count the number of valence electrons, right? And so valence electrons, as you recall, are electrons in the outer shell of an atom, right? It's just the outer shell. We don't care about the inner shells. So for hypochlorous acid, we have 1 hydrogen, 1 oxygen, and 1 chlorine, meaning we add 1, right, for the 1 valence electron in hydrogen, 6 for the 6 valence electrons in oxygen, and then 7 for the 7 valence electrons in chlorine. Do we also determine the charge like 1 plus to determine number of bonds? Can you kind of clarify your question? Are you talking about like how we would draw the Lewis dot structure of like an ion? Like a polyatomic ion? Yes, you are. We're going to get into how we handle that a bit later, since it would be on this step where we adjust the number of valence electrons we have if we have a positive or negative charge. So yeah, you're not wrong that we would add or subtract valence electrons to adjust for a charge, but we'll get to that a little later. So we've counted the number of valence electrons, and we found that in this structure, we're going to have 14 valence electrons. So when we see an even number, we're happy. We like even numbers, and 99 times out of 100, you're going to get an even number. So now that we've got our valence electrons, you're going to connect everything with single bonds, right? So you're going to take that H and bond it to the O, and take that O and bond it to the chlorine, right? And then you're going to count the remaining valence electrons. So you have to remember that a covalent bond, as we talked about earlier, is a shared bond between 2 atoms. So because of this, basically each line that you draw is 2 valence electrons that you're going to have to count out. So first, we connect everything, right? So 1, 2. So we formed our single bonds, and then we count our remaining valence electrons by just subtracting from the original total. So we know that each of these bonds is 2 valence electrons each, right? So 14 minus 2 times 2 is just 14 times 4, which means we have 10 valence electrons remaining, or 5 pairs, right? We're really going to be adding electrons in pairs more so than one by one, because of the fact that we're going to be completing octets using lone pairs. So that is basically what step 4 is for, distributing the remaining valence electrons to complete octets, right? So generally when we're drawing Lewis dot structures, we're following the octet rule, right? Which means that an atom wants 8 valence electrons in its outermost shell. There are exceptions to the octet rule, such as for elements prior to group 3 and after group 3. It's really a very shaky theory, but the octet rule really does apply for a lot. And when it doesn't apply, you'll know, because you'll either have extra or you will have not enough to complete an octet. And in that case, you'll know and be able to look at the periodic table and know that this is an exception to the octet rule. But luckily, we're not dealing with an exception to the octet rule. So we're going to distribute remaining valence electrons to complete our octets, right? And you want to add your valence electrons to the most electronegative element first, right? So tell me, what would be the first element that we give electrons to? Chlorine, exactly, right? With this one, chlorine and oxygen, it's kind of a grab bag. They both have very similar electronegativities, but it ends up working out in such a way that it works. But in general, you want to give to the most electronegative first and complete that octet because they're going to pull the most on the electrons. So we fill up chlorine's octet. So we have 1, 2 from that shared bond, 3, 4, 5, 6, 7, 8. So we've now filled chlorine's octet, right? We have 8 valence electrons. And so now we want to move on to the next thing that doesn't have a completed octet, which is oxygen. So oxygen has 1, 2, 3, 4 valence electrons right now. So we need to add another 4 to complete its octet. So 1, 2, 3, 4, right? So now we have filled the octets of all 3 atoms. A double bond might form between oxygen and chlorine. Well, we wouldn't need that here in this case, especially because chlorine, you're really generally never going to see no, you're not. Because think about it this way, we filled the octets of oxygen and chlorine, and so we really have no need to redistribute electrons in such a way to fill an octet. And next slide, we'll look at when you'll need to add double bonds. But for example, with chlorine, if you were to add another bond here, now oxygen would have 1, 2, 3, 4, 5, 6, 9, 10 atoms, which is overfilling its octet, which an atom like oxygen cannot do. Furthermore, chlorine generally will only form single bonds. So we will not be seeing a double bond in this situation, but it was a good thought. It's definitely a really good thing to be watching out for. Do we always have to calculate FC to determine double versus single? I'm figuring when you say FC, you mean formal charge. You don't really have to calculate formal charge. You'll just know, because we'll talk about in the next slide. You'll see situations where you can't fill an octet, and then you have to redistribute an electron pair to form a double bond. However, yeah, you might have a situation where you might have, let's say, a negative formal charge on something, and forming a double bond might reduce that formal charge to a 0, right? And that will make the Lewis structure more optimal, right? And we'll talk about later why you want to minimize formal charge. But yeah, formal charge and whether or not you have a double and a single bond are definitely highly related, but they're not directly causal, right? So here is step 5, right? If step 4 doesn't complete octets, create double bonds, right? So our example would be nitrous acid. So just drop in the chat which atom does not have its octet completed, right? Is it hydrogen? Is it oxygen number 1, nitrogen, or oxygen? Right, nitrogen. Exactly. So we see that nitrogen has 1, 2, 3, 4, 5, 6, right? And we also see that oxygen only has a single bond, right? And we see that if we distribute this electron pair here to form another bond, we get a double bond. And the reason we do this, and we'll talk about this later, is not only to complete the octet of nitrogen, but also again to reduce formal charge, which we'll be talking about later when looking at Lewis dot structures more in depth. But in general, you'll know when you can make a double bond. Typically, like oxygen will form double bonds. Oxygen's really the main one. So nitrogen will form triple bonds. Sulfur might form double bonds. So it's really, you'll know. It might be difficult now, but when you just, the real key to doing something like this is just to do practice after practice after practice. And that's what we're going to do, right? So here is an AP style free response question about Lewis dot structure. So it says, complete the Lewis dot structure of O2F2 shown below by adding in all of the electron pairs, right? So remember our steps, right? We count valence electrons, with single bonds, and then distribute our valence electrons. So I'm going to pull up a little whiteboard and show you guys how to do this step by step. So let me just close this out. Chrome tab. There we go. So we had it like this, right? F, O, So what is our first step when doing a Lewis dot structure like this? Do you recall, what was the first thing that we did after finding out the order that the atoms were bonded in? Electronegativity. Right, electronegativity is going to play a role. We found the most electronegative, right? It's going to be fluorine. But what do we have to do before we actually apply any valence electrons? We have to figure out how many there are, right? That's a step that a lot of people forget because they kind of think about the stereotypical bonding practices of certain atoms. And that definitely is going to be a shortcut for you guys in the future. But for now, definitely be sure to go step by step in terms of counting the valence electrons. And I'm just erasing this just to make it look prettier. It just wasn't big enough, and it was kind of spaced weirdly. So how many valence electrons are we going to find in fluorine? 7, right? So we have 2 times 7 plus 2, right? We have 2 oxygens times how many in oxygen? 6, right? So 2 times 7 is 14 plus 12 times 2 times 6 is equal to 26 valence electrons, right? So now our next step is to just connect everything, right? We want to connect everything with a single bond, right? So single bond, single bond, single bond, right? So how many valence electrons did we just use up by creating those 3 single bonds? We used up 6, right? Created 3 bonds each with 2 valence electrons each. So what we do is, just to keep track of things, we're going to cross out the 26. We're going to remind ourselves that we have 20 valence electrons to play with, right? So now is where we start talking about electronegativity. So where are we going to assign electrons first to complete octets? Which element? Right, think back to the trend for electronegativity on the periodic table. Fluorine. Yeah, exactly. You can hear my brother in the background doing whatever he's doing. So, right. So if we assign our valence electrons, we're going to want to complete the octets of both of these fluorines, right? So we have 2 here, so we need to add another 6 valence electrons, right? So we have 1, 2, 3. Let me make those bigger. Right, so we have 1, 2, 3, 4, 5, 6, and then we do the same here. 1, 2, 3, 4, 5, 6. And so now we have completed the octets for both fluorines, right? So we have 1, 2, 3, 4, 5, 6, 7, 8 for each of those. So now how many did we just use up creating those lone pairs? How many valence electrons? 12, right? So we're going to subtract 12 from this. Now we have 8 valence electrons to play with. And so we're going to assign those to the oxygens, right? So how many valence electrons do we have to add to each of those oxygens to complete their octets? So think about how many they have, right? 4, exactly, Hannah. So we have 1, 2, 3, 4, 1, 2, 3, 4. And that's the entire structure for difluorine dioxygen difluoride, I guess it would be called. That's kind of a weird molecule in general. But really, this will become second nature to you once you start doing a lot of these. You'll realize that seeing something like this with fluorine is pretty much the only thing you can see. And this with oxygen is pretty common. So you'll start to the kind of shortcuts that you can take when drawing Lewis dot structures, especially in things like oxygen, halogens, and stuff like that. So, rules with ions, right? I remember someone was talking about this earlier. So when we're trying to calculate the number of valence electrons for something like ammonium, right? You're going to subtract a valence electron for every positive charge and add 1 for every negative charge. So here, for example, we look at the ammonium ion, right? So that has a +1 charge. So we're going to find 1 nitrogen, 4 hydrogens, and then we're going to subtract 1 valence electron because of the fact that we have a positive charge on our molecule. And so that's going to be equal to 5 plus 4 times 1, which is 4, minus 1, which gives us 8 valence electrons. And then we just treat it like normal, right? We just create our bonds and apply our valence electrons. However, we realize that after we've created these 4 bonds, we don't need to add any lone pairs. Every octet has been satisfied. So that is really a generally easy one to look at. All right. And also, you might realize that if you guys know about formal charge, you might notice this nitrogen will have a +1 formal charge. And so we'll talk about later that there's a connection between formal charge and the overall charge on a polyatomic ion, such as ammonium. So now we're going to jump right into a very connected topic to Lewis structures, and those are resonance and formal charge, right? So resonance and formal charge are kind of side topics from Lewis structures, but they're incredibly important because they help to describe not only how molecules look and how they act. It helps to describe the charges applied to each atom and what happens when you can draw different structures, valid structures for a certain molecule, and how that affects bond lengths and bond energies. So, formal charge. So formal charge is the charge assigned to an atom in a molecule, right? So even if you have a neutral molecule, you might have times when an atom isn't bonded the ideal way it wants to, and so it will take on a sort of charge. And so, as I mentioned earlier, the sum of all formal charges in a structure add up to the molecule's charge. And this will make sense once we take a look at an example in a few minutes. So the formula for a formal charge for a specific atom is that you take the number of valence electrons it has, right? So for example, oxygen, it's 6, fluorine, it's 7, carbon, it's 4, and you subtract the electron count. And what the electron count is, and this took me a really long time to wrap my head around, it was the amount of bonds plus the number of lone electrons, right? Or 2 times the number of lone pairs. Really, what this boils down to is you're going to add up the sticks plus the dots, right? And we'll see how that, what that means in a little bit. Basically, the sticks being the number of bonds, and the dots being the number of lone electrons. So, taking a look at ozone, right? O3. We want to find the formal charge of each oxygen in ozone. So we have 3 different oxygens here, right? We see a double bonded oxygen, an oxygen with what is 3 bonds, and an oxygen with just a single bond. So let's start taking a look at these formal charges. So the formal charge will always be 6 minus something, because the valence electrons in oxygen is 6. So here we have 6 minus, I remember dots plus sticks. So we have 2 sticks and 4 dots. So that's 2 plus 4. So 6 minus 6 is 0, right? If we're looking at now this middle oxygen, we see that we have 6 valence electrons again. However, we have 3 sticks and 2 dots, meaning it's going to be 6 minus 5, which gives us plus 1. Then if we look over here, this one is one that you'll get really familiar with oxygen specifically. So usually you'll be able to just point this out. But if you wanted to calculate it, which we're going to, we do our normal 6 minus 1 stick plus 6 valence electrons gives us a formal charge of minus 1. So does that make sense? Why different formal charges are the way they are? All right, perfect. So when drawing your Lewis dot structures, you want to minimize formal charge. So this may be a reason why you create a double bond, because of the fact that you can minimize your formal charge by creating a double bond and still maintain your octets. So with ozone, for example, you see we can't really minimize this formal charge. However, just looking at these formal charges, what is the overall charge on the ozone molecule? Zero, exactly, right? you're going to see that you have 0 over here, then those +1 and -1 will just add to 0. So that's how the formal charge in an atom will, in a molecule, will always add to the overall charge of that molecule. So let's start talking about resonance. Right, so I'm going to stay on this slide for just a minute. Would it be unreasonable for me to say that we could swap the double bond for the single bond in this molecule? Basically just turn it upside down. Right, does that make sense? That you could essentially just draw this molecule backwards, right? There's more than one way to draw this Lewis structure, right? And you might start an argument and be like, hey, no, this is the double bond. No, this is the double bond. No, this is the double bond. And you can go back and forth and back and forth. When in reality, what resonance tells us is that both of these are the Lewis structure and that the Lewis structure is both of these. This is not a complete Lewis dot structure, and this is not a complete Lewis dot structure. This is the complete Lewis dot structure. And they'll tell you when resonance really is, they might not tell you, but it'll be obvious when resonance is necessary, because they might say, draw the Lewis structures of the nitrate ion or whatever. The thing with resonance is that you kind of get a blending of the two resonance structures, right? This is where resonance kind of gets a little hairy with some people in terms of contextualizing or conceptualizing. So we have our two resonance structures here, right? We have our double bond on the left, double bond on the right. When we blend these together, we get essentially 1.5 bonds, a 1.5 bond here and here. Meaning in comparing bond lengths, you want to kind of treat this as shorter than a single bond, but longer than a double bond. And same goes for bond energy. So that's really the important thing to take out of resonance, is that this will become a blending of these two resonance structures. Right, so does that make sense? Do you guys understand? Have any questions regarding resonance or how that all works? All right, you don't understand? All right, you do understand. Okay, perfect. All right, so let's move right on. So our final bit of this, right, in our last 8 or so minutes, is on VSEPR and bond hybridization. So really, we talked about what bonding is, how to draw bonds, how to model bonds, and now we're going to talk about basically what makes these bonds look the way they do. Why do certain molecules take on a trigonal shape, whereas others are tetrahedral? And what this boils down to is VSEPR, right? It boils down to, we want to get these electron pairs as far away as possible without inducing more repulsion, right? And with different combinations of electrons, that will differ. So, right, so there are a few things that you need to know about bonding before we get into VSEPR and hybridization. So we're going to talk about basically the major form of bond theory that is covered on the AP exam, and that is called the localized model of bonding. So there are two types of bonds, covalent bonds, according to the localized model, that being a sigma bond and a pi bond. Right, so a sigma bond is basically when two hydrogen atoms, or not two hydrogen atoms, when two half-filled orbitals overlap to create one full-filled orbital, right? So for example, we see these two half-filled 1s's form one fully filled orbital. So we see an SS sigma bond. And here with hydrochloric acid, we see the p orbital, the 3p in chlorine, overlap the 1s with hydrogen, forming an sp sigma bond. Right, and don't confuse it with sp hybridization, just sp, an s and a p with a sigma bond, right? So you might be wondering, well, what happens with double bonds, right? Well, that's where pi bonds come into play, right? So a pi bond is defined formally as a side-by-side overlap of orbitals parallel to the internuclear axis. So that might sound really scary, but really all it means is that when you have a double bond, you're going to have these p orbitals that are sticking out this way, right? And then if you have another bond, they're going to be kind of sticking out like that. Think about it like in 3 dimensions. And those p orbitals are going to have an attraction to each other in the form of a pi bond, right? So a sigma bond, we see this direct overlap right here. Whereas with the pi bonds, we see the p orbitals, these lone p orbitals, indirectly overlapping with each other, parallel to this internuclear axis, right? So this is where hybridization comes into play. So hybridization is really where atomic orbitals obtained, they're the atomic orbitals obtained when two or more non-equivalent orbitals of the atom combine in preparation for covalent bond formation. So really what this means is that when we're looking at covalent bonds, right, we're going to have to hybridize our orbitals because of the fact that if we look at methane, right, for example, CH4, we're going to see that this won't form 4 hydrogen bonds or 4 bonds with hydrogen because of the fact that we only have 2 half-filled orbitals. So the first step in hybridization is where we graduate one of these s orbitals to this empty p spot, right? So we have 1 half-filled s and 3 half-filled p's. Then what happens afterwards is that we hybridize, right? We take all these half-filled orbitals and we fill them, or we hybridize them into an sp3 hybrid orbital, which has 4 half-filled orbitals, which means we can form 4 sigma bonds. So that is really why hybridization matters. It helps atoms bond in a way they wouldn't be able to with just traditional s and p orbitals. So here we see what those 4 orbitals look like, where we have each of the 4 sp3 orbitals that, when put together, form a tetrahedral shape, right? So we see that when this happens right here, it forms each of these 4 individual orbitals, right? We have an sp3 facing this way, facing this way, facing this way, and facing this way, right? And so when put together, we get this whole tetrahedral model of the sp3 hybridized orbital. So when we're talking about molecular geometry, hybridization has a direct relationship, right? So let's just first start talking about VSEPR, right? VSEPR stands for valence shell electron pair repulsion. And all it basically states is that in a molecule, lone pairs repel each other to reduce repulsion. So it may sound a little weird, but basically, they will repel themselves just until they can get as far away from the others as possible. And that depends on what we're looking at, what type of bond we're looking at, and what type of orbitals we're going to be looking at. So we can see the general shapes are linear, trigonal planar, bent, tetrahedral, trigonal pyramidal, trigonal bipyramidal, and octahedral. Those you'll just kind of have to memorize in terms of knowing what they look like. But you'll be able to then also look at a molecule and say, all right, it's tetrahedral here, or it has a bent geometry here. So it's really something that you will get to know very well. And if you have really good spatial reasoning, you're probably going to find this relatively easy because of the fact that you can kind of manipulate things in your head and make it look right. So there's a distinction to be made, however, between molecular geometry and electron geometry. So molecular geometry is just what does it look like? If you were to like almost zoom in on this molecule, what would it look like? So that's what's shown in black here, right? We see the tetrahedral shape, the trigonal pyramidal shape, and the bent shape. However, when we take into account the actual electrons, right? When we take into account the electrons, that this lone pair is still there, meaning that in reality, this still has a tetrahedral electron geometry. Same goes for this bent molecule, right? It's kind of hard to represent in 2 dimensions, but you kind of have the 2 atoms together here. Then you'll have a lone electron pair right there and a lone pair there. And the reason we see different shapes is because according to VSEPR theory, those lone pairs will repel a lot harder than do just regular bonds. And so that is why we get shapes like trigonal pyramidal, bent shapes. We see the seesaw, the T shape, trigonal pyramidal, the bent shape, stuff like that. So another thing that we want to look at is how do you determine hybridization without going through that long-winded process of graduating the electron and showing how you get 4 sp3. You just look at the geometry. So there are 3 hybridizations you're going to have to know for the AP test: SP, SP2, and SP3. And they're all formed in the same fashion as SP3 was. So they're kind of, think about it in the same way. So when you have a linear shape, you're going to have SP hybridization, right? Meaning you're going to have some lone p orbitals hanging out right here and here. When you have trigonal planar, you have an SP2 shape. And then tetrahedral, you have SP3. And when we look at the hybridizations, it's based off of electron geometry. So for example, in water, right, what would be, here, I'll pull up this whiteboard again. Right, so I'm going to draw a structure. Now tell me what the hybridization around oxygen will be. Right, so there we go. So if I just draw you, if I draw you this. So we have water, and I'm going to draw in oxygen's lone pairs. Just 1, 2, 3, 4. So what is the hybridization about the oxygen, in this situation? Right? Think about the electron geometry, not about the molecular geometry. All right, so Hannah says SP. It would be SP3. Because if we try to look at the geometry about this oxygen, we can see that we're going to see this hydrogen here bonded to the oxygen. We're going to see that hydrogen there bonded to the oxygen. And then you're going to have this lone pair right here. And then you're going to have a lone pair right here. So therefore, the electron, okay, you didn't take the electrons into account. Exactly. You want to always take the electrons into account when looking at hybridization, right? Especially, it might throw you off that, the only time you'll see sp hybridization is if you see a straight, a bond, right? It has a tetrahedral electron geometry, yeah. So what would be the actual hybridization of that oxygen atom then, based off of the fact that it has a tetrahedral electron geometry? Just take your best guess. So it's not sp. So it has a tetrahedral geometry. So what can that tell us about the actual hybridization of this oxygen atom? Yes, it is sp3. Because of the fact that we have this tetrahedral geometry here. Right, so if we look at, for example, in here it would be the 2p orbital, right? We see that we're going to see an sp3 hybrid orbital with 4 half-filled electrons, right? We're going to see one of them here, one of them here, one of them here, one of them here. And so that's why we're going to see sp3 hybridization whenever we see tetrahedral geometry. So when we're looking for hybridization, all you have to do is look at what it looks like. If it's linear, it's sp. If it's trigonal planar, it's sp2. Tetrahedral, sp3. And those are the only 3 hybridizations you need to know. Your teacher might teach you something like sp3d or sp3d2 for the AP exam. You do not need to know those. They will not address the d-based hybrid orbitals on the exam. They'll only ask you for those 3. So here's a quick example question, right, based off what we just talked about. So first part is to count the number of sigma bonds and pi bonds in the structure of acetic acid shown. So for example, a single bond will be a sigma bond, and when we're looking at a double bond, we'll have a sigma bond, and then that double bond, that second bond is a pi bond, right? You can only have one sigma bond per bond because you can't have multiple directly overlapping orbitals. So the other part will be a pi. So you say 5 sigma 1 pi. So 1, 2, 3, 4, 5 sigma 1 pi. Perfect. All right. 5 1 pi. It's a perfect answer. Couldn't have said it better myself. So now I'm asking you, what is the hybridization, and I'm going to say molecular geometry, about the rightmost carbon? So we're focusing on this carbon for now. So just tell me, what is the hybridization and geometry? And this might be a little harder to kind of think about, kind of try to simplify it down in such a way that you can visualize it. So Hannah, you're saying tetrahedral sp3, right? Anyone else have any other guesses? Anything else to add? Perfect. All right. So, right, perfect. We're going to see around this leftmost hydrogen, we're going to see a tetrahedral molecular geometry, and therefore an sp3 hybridization, right? So now let's look at this, this rightmost carbon. I kind of screwed that up and switched those questions, but it's the same question. We're looking at this carbon. What would be the hybridization and the molecular geometry about it? Let's take a guess. So Samuel says sp2. Okay. So what would be the geometry? Maybe linear or bent. sp3 because of the electron lone pairs on the oxygen. Okay, so we're looking at this carbon. So kind of we're looking at the geometry about one atom. We're not really going to care about what's going on with the lone pairs on the oxygen or the lone pairs here, due to the fact that we just want the geometry about that carbon. So it isn't going to be linear or bent, right? We have 3 bonds here, right? The 1, 2, and 3. And we see that we have no electron pairs on the carbon that we're going to see. So we're going to see, yes, trigonal planar geometry, right? And we know that it can't be anything like tetra because of this double bond, right? We're never going to see double bonds in a tetrahedral geometry. So Samuel, you were correct earlier in saying that this was sp2 hybridization, right? We see sp2 hybridization, and that's why we have room for this double bond here, because when we have sp2 hybridization, we're going to have is tetrahedral the expected hybridization? Matthew, can you kind of explain your question? I don't quite understand what exactly it is that you're asking. But yes, when we have sp2 hybridization here, we're going to have one lone p orbital that's going to form a double bond with that oxygen. So we're going to kind of wait for the expected versus actual. I don't really know what you're referring to, especially with hybridization. Are you referring to, is it something that I went over regarding like electron geometry? Okay. Yeah, I don't really understand what exactly it is that you're asking about. So that's it. That's unit 2. I know that was probably a lot of information that I kind of just shoved in your brains in an hour and 10 minutes. So just last minute, any questions about unit 2, about AP Chem, really about anything? I'm happy to go over any questions that you guys have in general about chemistry. Is unit 3 gas laws? Unit 3 is, let me pull up the CED. I believe unit 3 does have the gas laws in it. But yeah, I think Hannah, you're correct in saying that it is intermolecular forces. So Hannah says, so there are linear, trigonal, and tetrahedral. There are a ton of actual shapes in terms of molecular geometry. There are a ton. There's linear, trigonal planar, bent, tetrahedral, trigonal pyramidal. There's trigonal bipyramidal. There is T-shaped. There is seesaw. You kind of have to look them up. I can try to find a picture, actually. Wait. It might not look that great on the slides, but I'll try to find an image of every single VSEPR shape for you. There we go. Here's a good one. There we go. So these are, right, and I'll get to your question in a second. So here's every single type of geometry, molecular geometry. And you might see that these are repeated. So we have a couple bents, we have a couple linears, a couple trigonal planars. But those are generally the ones you're going to see. The most popular ones that you're going to see are going to be trigonal planar, tetrahedral, linear. You might see a T shape here or there. It's very rare that I see something like square planar, however. Okay, Hannah asks, can you explain polarity with versus non-polarity with intermolecular force like, I'm assuming when you say IDHP, do you mean like induced dipole forces? And dipole forces, yeah. So here, let me pull this up again. And I'm just going to pull that up. London dispersion. Okay. Yeah, so that's the same thing as an induced dipole attraction, which I'll talk about in just a second. So remember earlier we were talking about what makes a molecule polar in terms of its structure, right? It's that it's symmetric, right? So take, for example, methane, right? If I draw out the structure of methane, right, so CH4, this is a non-polar molecule because of the fact that we're going to see these dipoles heading like this. And they're going to cancel out, right? This and this and this and this. So we're going to see a general no polarity on this molecule. So that means that when two methane molecules find each other, there's going to be no real electrostatic force between them, right? There's going to be no like positive negative attraction. However, that doesn't mean that there's no attraction whatsoever. When we have something like methane, those electrons, yes, they're shared relatively equally, but there are random moments where you might see a very instant partial negative form here and a partial positive form here to form an induced dipole, right? For just an instant. It's going to be incredibly random. These aren't consistent, which will form some form of an attraction. And that's what a London dispersion force is. And they're the weakest type of intermolecular force. And when you're looking at something like that, an induced dipole, you're going to talk about in your class something called polarizability. Essentially, how can you gauge how strong a London dispersion force is? So, for example, if we're talking about the forces between, say, a Cl2, right? So two Cl2s versus two F2s, right? You're going to learn how can we actually gauge how strong these are using the principles of polarizability. And you'll learn about that later in future streams, so I won't get to that right now unless you specifically want me to talk about polarizability. So now let's look at a polar molecule, right? Let's draw just a simplified structure, so no lone pairs of water, right? So here's water, and I'll draw a couple other waters just for sake of demonstration. There we go. Perfect. So here we have a polar molecule, right? We're going to see that oxygen is much more electronegative than hydrogen. So those electrons are going to be consistently pulled in oxygen's direction, which is what differentiates a London dispersion force from a dipole-dipole force. So we're going to see a partial negative charge on that oxygen and a partial positive on those hydrogens. There's a partial negative, partial positive, and I'm just going to draw them all in. And so what we're going to see is much stronger and much more defined attractions between these negative parts of the water and these positive parts of the water, which forms much stronger attraction between the dipoles. Does that make sense? Do you understand that? Perfect. All right. Do you have any other questions from anyone about chemistry, about anything we talked about tonight? I know I kind of just gave you a quick preview what our next stream is going to be on. But, all right, so if no one has any more questions, I think we're done for the night. So I'm going to hang out for just just for a minute or two more, maybe 30 seconds, just to see if anyone else drops a question, and then I will head on out. So I think it doesn't look like anyone else has any more questions. So I'm going to sign off for the night. So have a great night, and good luck in your chem class.